Synchronous machine part 3. Topics in these slides will be external characteristics of synchronous generator. Sometimes it is called as output characteristic. Let me write it down here. Output characteristics. In some books it is also said terminal characteristic of synchronous generator. Okay, compounding curves, another characteristic, V curves, and on-grid operation or parallel operation. Parallel operation synchronous machine is sometimes called as on-grid, şebekede demek. On-grid, şebekeyle birlikte. On-grid operation of synchronous generator. And then active and reactive power control. In fact, we know some about this, but we will repeat again. And then we will talk about motor startup methods. Let's start with terminal characteristic or output characteristic. That is the general connection diagram for conducting experiments. For example, if you apply some mechanical power in terms of torque and angular speed, which is synchronous speed always, and then you can have some measuring instruments for the required parameters. Here are load banks, adjustable. By having these circuit breakers or switches, you can choose related loads. For example, you want to apply some capacitive load, just switch S4. If you want to conduct something with pure capacitive load, please switch off S2 and S3, only switch on S4. In such a case, generator will be loaded by only capacitive loads. The other ones are similar. Here is the DC field voltage, applied to terminals. Here is a circuit breaker, and then here is a control rheostat field of generator, RFG. That is the controllable device to control field current. Here's ammeter to measure field current. Here's wattmeter measuring total power exchange. Here's the ammeter measuring line current. Here you see line current. Here's the voltmeter measuring line to line voltage between phases, because you only see three-phase terminals, not windings right now. Okay, that is the general connection diagram for synchronous generator experiments. In fact, we have already conducted open circuit test and short circuit test. Again, in short circuit test, for example, you can easily handle, let's say, here is a switch, but you should take care. It would be dangerous under rated voltages. That's for short circuit test. For example, first of all, please increase RF to infinity and then decrease. In the beginning, field current must be 0, then switch on, short circuit switch, and then decrease field rheostat and increase field current, and observe field current versus short circuit current. That is a straight line short circuit characteristic. Okay, today we talk about external characteristics or output or terminal characteristics of synchronous generator. First of all, let's discuss what it is. What they are. What is output? Now, we talk about generator. External or output or terminal characteristic of synchronous generator. Now, here's the generator, synchronous generator, having a star or delta connection, having 3 phase, and here you see 3 phase terminals, okay, UVW, and then here's a mechanical exciter, which is prime mover. You apply mechanical power in terms of torque and angular speed, but rotor angular speed is always kept constant. It is rated synchronous speed, so rotor speed is constant. So applied mechanical input power can only be adjusted by changing or adjusting applied torque to the shaft. Now, here's the system. That device, when you apply mechanical input power, will convert that power into electric power. But as a generator, here would be some reactive power as well. So, I mean, there would be some apparent power. Okay, input is a power. Output will be sum of active and reactive powers, or shortly apparent power. Okay. On the terminal, here are the electrical terminals. On the terminals, you observe some voltages. Let me say line to line voltage. Here you see on the terminal I1L, line current, line parameters in terms of line values. You observe line parameters, and then see, machine has 3 phase, but your machine has a 1 phase equivalent circuit. So here is a, let's say, 1 phase equivalent. Inside 1 phase equivalent, here you observe 1 phase voltage and 1 phase current, which is I1. That is 3 phase. That is 1 phase equivalent. Inside 1 phase, excuse me, I can show you like this. Here's the box. In the box, or across the box, you observe such a voltage and such a current at the terminals. At the terminals. And then inside the box, here is resistance, here is reactance, and here is EMF dependent voltage source. That's it. Since machine has one phase equivalent, we always discuss one phase parameters. And you see terminal parameters are V1 and I1. Those are phasors, of course. If you choose this guy reference, that guy will have such a phase angle with respect to reference, which is voltage. Phi is the angle from voltage phasor to current phasor, you know, because we always choose voltage as a reference. Now, ladies and gentlemen, what is the terminal characteristic? What is the terminal characteristic? Terminal characteristic is the relation between across parameter and terminal flow parameter, let me say versus across parameter versus flow parameter at the terminal. What does it mean? Here is one phase system, here is one phase voltage, here is one phase current of the generator. V1 is the across parameter, uç değişken. I1 is the flow parameter, flow, akan şey parameter. So, what is the relation between those two parameters? Please draw V1 versus I1. That is the terminal characteristic. You observe such parameters across the terminal and you examine on terminal parameters. I mean, here is current. Current affects, changes voltage. Voltage has some change due to current, and what the relation is. That is terminal characteristic, output characteristic, or external characteristic of synchronous machine. Some books say different. I recently prefer terminal or output because at the output of a generator you use some power. Power has some parameters such as voltage and current. Here would be square root blah blah, it doesn't matter. Across parameter versus flow parameter at the output will give you output curves or output characteristics. And now let me show you. Also terminal VI characteristics are called. To conduct such an experiments, we need to satisfy some requirements, which are speed. Rotor speed must be kept constant. Its synchronous value must be constant, kept constant, and then field current must have such a value, IFO is the field current when there is no load, and terminal voltage is its rated value. I mean, let me show you. First of all, here were the characteristic circuit, and then first of all, see, when there is no load, all the switches are off here on load banks, and then apply DC field current, keep speed constant by changing field rheostat, adjust field current at a field FO, a certain value. This value is a special value maintaining rated voltage here when there is no load. Here is no load, all the switches are off, you observe rated voltage, let's say 400 volts, and then that is the current to have 400 volts, for example. Okay, that is the field current when there is no load and the voltage is such a value. And then conduct loading under constant power factor. Houston, here is the load bank. You can adjust loads, but power factor will change. For example, if it is only S2 is on, this load will be pure ohmic. If there is S2 and S3 are on, in such a case, load is a mixture of R and L, so current will be lagging. During such a test, the ratio of XL over R, which is, I mean, the phase angle, must be kept constant. I mean, power factor must be kept constant. So first of all, it is easy to conduct such an experiment. First, apply pure ohmic load, and then apply pure inductive load. Here you see pure ohmic load, power factor is unity. Here in the second case, power factor is 0, lagging. As a third case, finally, apply pure capacitive load, again having a power factor of 0, which is leading. Current is leading. So repeat the experiment at least 3 times. Initially, here you see I1 versus V1 versus I1. But remember, you measure line-to-line voltage and line current. So consider whether the machine is connected star or delta, and then by using line parameters, decide how to use square root 3, and then calculate V1 and I1, and then draw the diagram. First of all, it starts from rated value. I1 nominal. Here it is. When there is no load, 0 load current. And then apply pure ohmic load. Voltage will drop, voltage will drop. Okay, let's say I want rated value. That is the curve belonging power factors unity pure ohmic case. And then apply pure inductive load. Power factor is 0, pure inductive or lagging. I prefer lagging. Inductive or lagging. And then apply pure capacitive load. Power factor is 0, pure capacitive or leading current load. Houston, of course, as you see, there are infinite number of choices. Here would be 0.9 capacitive, 0.8 capacitive, 0.7 capacitive, and then here would be 0.9 inductive, 0.8 inductive, blah blah. But the curvature is like this. That is called as thermal characteristic. The reason behind that voltage change, the major reason behind the terminal voltage change is armature reaction. Now remember, in pure ohmic load there was slight decrease due to armature reaction, but in a pure inductive case there was a dramatic decrease, and in pure capacitive case there were dramatic increase due to armature reaction. So we conduct a output characteristic to examine armature reaction effects, or observe armature reaction effects. You know what armature reaction is, what the result would be, but we observe armature reaction effects experimentally by conducting external characteristics. Okay. And here are some further topics. Compounding curves. Türkçe'de ayar karakteristiği diyoruz buna. Türkçesi ayar karakteristiği. Biraz farklı. Yani kompansasyon gibi oluyor. Şimdi buna da Türkçe'de dış karakteristik diyoruz. Onu da söylemiş olayım. Dış karakteristik. Makinenin dışarıya ne çıkıyor? Output diyorduk ya. Dış karakteristik. Tabi terminal kelimesi biraz İngilizce olduğu için sevilmemiş. Aslında terminal karakteristiği, yani uç karakteristiği her şeyde aslında daha genelleştirilmiş bir şey. Yani ben çok seviyorum o kelimeyi. Ayar karakteristiği, compounding curves. Requirements again. Requirements. How many minutes? We have approximately 20 minutes. Okay. Terminal character requirements are, first of all, During the experiment, keep terminal voltage constant. During the experiment, you should keep terminal voltage constant. Is it possible? Okay, here you see, when you apply some loads at different power factors, you observe some change in the voltage across the terminals. Now, please, ladies and gentlemen, find a method to compensate that voltage change, to keep it constant. What would be the method to keep terminal voltage constant? You should keep it constant. Again, rotor speed must be kept its synchronous value constant during the experiment, and then observe field current versus, or as a function of one phase armature current by changing load current at constant power factor. Again, here you see, here are multiple curves. Each curve belongs one power factor. So during the experiment, you should keep power factor constant when you are changing load. Okay, for example, first of all, you decide to conduct that experiment by applying some ohmic load. So switch on S2 only, and then change load and observe field current versus I1. That is the compensating curves, compounding curves. All those are the same, compounding curves. Yani eksikleri tamamlama eğrileri bir anlamda, tam kelime tefsiri olarak bakarsan, ama ayar karakteristiği, nasıl ayar yapmamız lazım, yani Türkçe söyleyecek olursam, yani çıkış gerilimini sabit tutmak için nasıl bir şeyler yapmam lazım. Elindeki kontrol parametresi, burada tork bitti, hızlan bir şey yapamazsın, o zaman uyarma akımı. Zaten adam diyor sana, diyor ki uyarma akımı yük akımıyla nasıl değişecek, gerilimi sabit tutmak için diyor. Ama diyor deneyi diyor sabit power faktörde icra et diyor. Okay, let me explain what the results are, and let me use the same color, blue, for ohmic loading. Okay, first, when there is no load current here right now, Houston, excuse me, to keep terminal voltage constant at its rated value, V1 rated. Okay, let me write it, V1 rated. V1 rated. Beep, beep, beep, beep. Excuse me. Oh my gosh. Here's field current, first of all, and then here's IFO. You know what IFO is. IFO results in V1 rated nominal at no load conditions. You previously know this. So IFO adjusted. During the experiment, voltage is kept constant at its rated value. Now, ladies and gentlemen, we have decided conducting experiment under pure ohmic load right now. So under pure ohmic load, you see there is a slight decrease in voltage. So we should compensate this voltage drop. Ta-ta. Excuse me, let me repeat it again. That is the compensating curve for power factor unity. Here you see some voltage drop depending on the load current under pure ohmic loading conditions. So to keep voltage constant, you should compensate that voltage drop by increasing field current. Here you see how to increase field current to keep output voltage constant. Okay, and then let me choose the same color, green one. There is a dramatic, strong decrease under inductive loading conditions. So to compensate such a dramatic voltage drop, you should increase field current dramatically. That is the curve for power factor unity lagging. I mean inductive loading case. And then here you see some voltage increase in capacitive loading. Power factor is 0 again in purple. Here it is. To compensate voltage drop, you should decrease field current. That belongs to power factor unity, leading current load. You can also say capacitive loading conditions. And then you know that there are some additional curves, power factor 0.8, let's say 0.6, 0.4 for example. And then here would be some other curves, 0.8 lagging, 0. Excuse me. Here is 0.8, 0.6 and 0.4. You are 1 here, so 0.8 is here. Okay, those are called as compounding curves. Those are the strategy to change field current to keep terminal voltage constant. We make some compensation. Those are compensating curves. Okay. We'd better stop here. Okay. Here are some animation. Let me click the animation. Perhaps. I couldn't find the animation. I don't know. Let's talk about the tendency of the curves. Tendency. Those curves will be like this. In the future, again, this will be up. But you should know that here, somewhere here, rated current is somewhere here. It is much more later. Okay. Please do not confuse. I clean here. It looks like this on the left hand side. Compounding curves looks like this. Terminal curves look like this. Okay. Slight decrease in ohmic loading, slight compensation requires in ohmic loading. There is a strong decrease in inductive loading. In green one, you see there's a strong dramatic decrease in voltage. So there must be dramatic compensation. Here you see. You should increase field current to compensate that voltage drop. That's enough for today.